Every day we face issues that implicate us in scientific claims. Should we vaccinate our children? Are genetically modified crops safe for us to eat and safe for the environment? And what can we do about climate change? And sometimes the science around these issues seems rather uncertain, so we just heard that a moment ago. Now, scientists work at the boundary between the known and the unknown, so I would argue that there is necessarily always uncertainty in active scientific research. But to some people, this uncertainty may seem like grounds for doubting the science. After all, if scientists can't tell us for sure what the answers are, then why should we trust science? And why should we act on scientific information? As many of you know, in my book, Merchants of Doubt, which I wrote with my colleague Eric Conway, we also documented and chronicled how uncertainties have been cynically exploited by those whose political or economic interests are threatened by scientific findings, and not just about climate change, but on a host of different issues. So how can we sort this out? And how can scientists speak up about their own science in a way that doesn't fall into the trap of naive realism? So I want to argue today that to accept the safety of vaccinations or the reality of climate change, we have to accept the claims of science, constructed or not. We have to believe in science. But scientists don't like to use the language of belief because for them it sounds a little bit too much like faith, and faith, of course, is the domain of religion. And science is supposed to be different from religion. In fact, many scientists see it as the opposite of religion. And so the language of belief is uncomfortable for most scientists. Moreover, when we think about belief, I always think about Pascal, one of my heroes, and his famous wager, in which, as most of you know, he fretted and worried about the issue of whether or not he should believe in God, having failed to prove the existence of God mathematically. And Pascal famously determined or decided that the risk of rejecting belief in God was greater than the risk of accepting it, and therefore, as one of my colleagues put it in university, he clutched for the handrail of faith. So this leads to an interesting question. Is science actually a leap of faith? The fact is that most of us do not know how to judge whether or not scientific claims are true. Rather, like Pascal, we assume that the risks of accepting science are smaller than the risks, accepting science are smaller than the risks of rejecting it. And so most of us do accept scientific findings. And it's very interesting in the United States, there's been so much fussing made about American rejection of science. But actually, if you look closely at the opinion polls and the data we have from social science research, you find that actually the majority of Americans accept the majority of science. So Americans don't have any problem with plate tectonics or with the existence of DNA. They only reject science in specific cases where they feel that it conflicts with their worldview, and the two obvious ones are climate change, which conflicts with people's belief in free market economics, and evolution, which conflicts with some evangelical Christians' literal readings of the Bible. Now, it's important for us to acknowledge that we're not just talking about, quote, ordinary people. Even most scientists have to accept results outside their own fields, essentially on faith. So a physicist is not really familiar with the evidence of evolutionary biology, and an evolutionary biologist is probably not really familiar with the details of climate science. And experts in any one field necessarily lack the expertise to judge evidence in another. In fact, I would argue that the specialization of science actually makes them even less able to judge than some other people might be. And when they try to judge, like when physicists try to judge climate science, we often find that that doesn't work out very well. So the big question I have posed in my own work in recent years is, should we trust science? The traditional answer to that question is yes, because it was held for many years. Scientific knowledge is true, it is warranted, it is valid, it is reliable, because scientists use a particular method that guarantees the accuracy of their results, and that method, it was often in the past said, was the scientific method. So if you were taught the scientific method in school, most likely it went something like this. This is what you would find in most high school textbooks in the United States if they talk about scientific method. And it would be what philosophers call the hypothetico-deductive method. We develop a hypothesis, we deduce its consequences, And then we go out into the world to observe those consequences, or in the laboratory, and if they're true, we're happy and we move on. We accept the scientific claim. Now, scientists do sometimes do this, and there are some very famous examples in the history of science where we can identify scientists using the hypothetico-deductive model. The most famous is the test of Einstein's theory of general relativity. In the theory of general relativity, the theory is that gravity, or what we have previously identified as gravitational attraction, is actually the bending of space-time in the presence of massive bodies, like our sun. So if light travels near the sun, it should, in fact, the rays of light would not travel in a straight line, but they would be bent along a curved path of space-time. Well, this was a rather startling prediction, totally different than the predictions of Newtonian mechanics and classical optics, and it was tested in 1918 by an expedition led by Sir Arthur Eddington, who tested it during a major solar eclipse. And indeed, he found that the evidence from the eclipse showed that starlight was bent in the presence of the sun. This was such a revolutionary finding that it was actually written up in newspapers around the globe, including this article from the Times of London. Now, sometimes philosophers refer to this model of science as the deductive nomological model. Nomological because in the ideal case, we're not just developing a hypothesis, we are searching for the universal laws of nature. So in this case, we conceptualize a law, but again, we deduce its consequences, and we look for those consequences, and if true, we are happy and we move on. And of course, Einstein's famous equation, E equals mc squared, is a good example of this, a general universal law that should apply in all times, all places, and under all conditions. The problem with the hypothetico-deductive or deductive nomological model, besides as a historical claim, which I'll get to in a moment, as a logical claim, it actually does not work. And the reason it doesn't work is because of something that philosophers call the fallacy of affirming the consequent. Just because a prediction turns out to be true does not prove that the theory that made it is true. The reason is that false theories can make true predictions. The most famous example of this in the history of science is the Ptolemaic system of astronomy, which, as you know, was widely accepted in the Western world for centuries before the development of the Copernican model. The Ptolemaic system made highly accurate predictions of the motions of the planets and the timing of celestial events, such as solar and lunar eclipses. In fact, its predictions were more accurate than the Copernican model when the Copernican model was first proposed. So this is an example that shows us that even though in hindsight we would say that the Ptolemaic system was conceptually incorrect, it nevertheless made accurate and true predictions. So a false theory can make true predictions. The second problem is the problem of auxiliary hypotheses. When we test a hypothesis, we are not just testing that hypothesis alone, but we're also testing various other assumptions that are built into the test. So beliefs don't exist in isolation. The American philosopher Willard Van Orman Quine wrote extensively about the idea of a fabric of belief, that our beliefs are intertwined with other conceptual commitments, and when we make a test, those other hypotheses, those other conceptual commitments are implicitly being tested as well, even though we may not think so. We're also testing the reliability and the sensitivity of our instruments. So again, if we go back to the Copernican model of the universe, when Copernicus proposed the heliocentric model to replace the Ptolemaic one, many scientists said, well, that's fine. If the Earth is moving, we should be able to detect the effects of that motion. One of the effects that scientists, particularly astronomers, predicted was the effect of stellar parallax, the change in the apparent position of stars as the Earth moves through space, through its orbit. So this is a simplified diagram illustrating the idea. As the Earth moves through its orbit from December to June, we could look at a bright, distinctive star like Polaris, and in June, we would see it against a different backdrop than we would in December. And that angular distance between those two rays is the stellar parallax. So astronomers did this test. They looked for the stellar parallax, and they found nothing. So you might conclude, therefore, that the Copernican theory was incorrect. Well, today we would say that those scientists were implicitly invoking an auxiliary hypothesis, namely the assumption that the Earth's orbit is large relative to the distance to that distant star. We would now say today that that assumption was false, that actually the Earth's orbit is tiny, and therefore the stellar parallax is tiny relative to the distant stars. So therefore, they failed to detect it because they were making a wrong assumption about the scale on which these activities were operating. Moreover, they were also implicitly assuming that their telescopes were sensitive enough to detect the parallax. In fact, it was not until the 1850s and the work of Sir William Herschel in which telescopes were adequate enough to be able to detect the parallax. So if we had waited for this test to be true, we would have had to have waited more than 2 centuries. So we might say that the hypothetical deductive model is an oversimplified picture of what scientists do and what the scientific method is. But actually, it's worse than that, because a good deal of science just doesn't follow the deductive model at all. A good deal of science is inductive. And by that we mean that scientists start with observations. They don't necessarily start with theories or hypotheses. They might simply go out into the world and make observations and then generalize from those observations. In the Sherlock Holmes stories by Arthur Conan Doyle, this is famously what Sherlock Holmes does, even though in the books he claims that what he's doing is deduction. Actually, what you see in the structure of the story, he observes details of the world around him, and from that induces what actually transpired. Now, the interesting thing about inductive science is that in the mid-20th century, inductive science would go out of fashion. Many scientists rejected induction as the appropriate method. The great physicist Ernest Rutherford famously or infamously dismissed it as stamp collecting. And this idea was promulgated particularly by many American physicists who tried to promote a more hypothetical deductive model of science than had been previously accepted. But actually, if you look at the history of science, some of the most important work in the history of science was, in fact, inductive. And the most famous example, of course, is Charles Darwin and his work on the origins of species through natural selection. When Darwin went on the voyage of the Beagle, he did not have a hypothesis in mind. In fact, he frankly confessed to his friends and colleagues that he really had no idea what he was doing, that he was quite frightened and nervous, but he was optimistic that if he kept his eyes open and carefully and accurately recorded what he saw, that he would learn something in the process. And of course, he famously did. And he became a hero to several generations, particularly of English-speaking scientists, who believed that he had demonstrated that this was, in fact, the correct way to go about doing science. Darwin was particularly influential among geologists because he himself was trained as a geologist and identified as a geologist. And this way of thinking was extremely influential in the United States and had an impact on the debate over continental drift in the early 20th century. When the German geophysicist Alfred Wegener first proposed the theory of continental drift, he was criticized by American scientists for many things. But the thing he was criticized for most harshly was that his theory was not inductive, that he had begun with a theory, a hypothesis, and then looked for evidence to support it. So this is, of course, very ironic because later many people would say that inductive science was bad, but here we see scientists saying that deductive science is bad. Indeed, the defenders of continental drift theory in the United States tried to emphasize its inductive base. And they wrote articles in which they said, well, look, Wegener himself might be prejudiced by his theory, but the evidence actually existed before Wegener ever came on the scene. It was drawn from well-established scientific traditions such as stratigraphy and paleontology, and it had been collected by highly respected earth scientists around the globe, in Europe, in America, in South Africa, in South America, over decades. So inductive science is another scientific method. A third scientific method is modeling. This consists of building models to test hypothetical ideas. So this is a photograph of the 19th century, late 19th century geologist Henry Cadell, who was very interested in the question of mountains, the origins of mountains, and particular in the origin of the great thrust faults that we see, for example, in the Alpine nappes, where large bodies of rocks had clearly been moved great distances. And so in this case, he built a physical model as a kind of test to see whether or not you could get these kinds of structures in rocks through horizontal compression, which is being modeled in this apparatus here. And you know he's a geologist because he has a wheelbarrow and he's wearing Wellington boots. Now, in the 19th century, models were typically physical models. In the early 20th century, sometimes people built electrical models, but in the later part of the 20th century, models became mostly numerical simulations. Climate change is one area, but not the only, in which numerical simulations have become extremely important for testing causal theories. So this is an example of an important kind of simulation in climate science in which scientists ask the question, if the black line at the top represents the observed changes in mean global surface temperature since the year 1900, then what combination of factors best explains what we see? And the answer to that question, derived from numerical simulation modeling, is greenhouse gases. We know there are many factors that can influence the temperature, but the only one that can explain the large increase in mean global temperature over the last 50 years is the increase in greenhouse gas concentration. If you try to model the atmosphere without greenhouse gases, you would simply see a more or less flat line or even a little bit of cooling because the influence of other pollutants like sulfate aerosols or dust in the atmosphere from volcanoes is mainly to cool the planet. It's only the greenhouse gases that drive it in the direction of warming. So observing that scientists, in fact, follow many different kinds of methods, the mid-20th century philosopher Paul Feyerabend once said that if there is a scientific method, it is anything goes. Now, this is often quoted out of context to imply that he was some kind of epistemological anarchist, but actually, Feyerabend was not actually saying that anything goes. What he said was, if you press me to say what the method of science is, then I would have to say that the only principle that does not inhibit progress is anything goes. So Feyerabend was in fact saying that the methods of science are diverse, that scientists are creative, and they have used different methods to good effect. But then this leads to the question, do these diverse methods have anything in common? Is there any common theme in all of this work? And I think there is. And I think it's evidence that all of these diverse methods are means of collecting, generating, and creating evidence. I would argue then that evidence is the key element in scientific knowledge, not method, and that we've been mistaken in being overly focused on method and really should be paying more attention to the questions of how evidence is generated and what constitutes good evidence versus bad, or as the philosopher Nancy Cartwright says, what makes evidence evidence? The question I want to look at, or I have looked at in my work, is the question of who judges the evidence. Because the answer to that, I think, is very clear. It's scientists. So this then leads in turn to a different question. How do scientists decide when they have enough evidence to say that something is known? And the answer to that is consensus. And so my work on the scientific consensus on climate change was partly driven by simply wanting to answer the question, is there a consensus among experts about this matter or not? So I would argue that scientific knowledge is the body of claims that have been agreed upon by relevant scientific experts. Claims that experts have concluded are supported by sufficient evidence to say that they are true. Now, this conclusion troubles some people because it may seem as if I'm saying that science is just an appeal to authority. So I want to make a slightly controversial claim that actually science is based on the appeal to authority, but it's a particular kind of authority. It's not the authority of an individual, no matter how brilliant or wise that individual may be. It's not the authority of a lonely or celebrated genius. But it's the collective authority of diverse experts who have weighed and judged available evidence. Now, I obviously chose this picture because it shows a very diverse group of scientists. I have to say, I'm sometimes a little skeptical if these people are really scientists because they look too happy. But nevertheless, we can still conclude that scientific knowledge is the intellectual and social consensus of affiliated experts based on the weight of available empirical evidence and evaluated according to diverse but time-tested methodologies. It's a kind of jury, but a very special one, a jury of scientific peers. Other analogies you can think about, in a way it's like a kind of crowdsourcing, except it's a very specific kind of crowd where the people who have input are people with PhDs. And this is, I think, one reason why the internet has become such a problem for science, because so many people can now weigh in and post things that appear to be scientific, even when they actually are not. I have one other analogy that I developed a long time ago, but I'm particularly happy presenting here at the Volkswagen Foundation. It's the analogy of a car. Now, many people think there's a strong distinction between science and engineering, but I want to argue that actually the reliability of science is similar to the reliability of the modern automobile. The modern automobile is an incredibly reliable technological device. You get up in the morning, you turn on the key, and most of the time it works. But it's not reliable simply because of the genius of an individual like Daimler or Benz or Ford, but because the modern car is the product of hundreds or even thousands of scientists and engineers who have worked on it to produce this vehicle over more than a century. And I have to, of course, end with a plug-in hybrid, although I really prefer fully electric cars, but in any event, that's a nice picture. So why should we believe in science? The answer, I think, is because our scientific knowledge is based on the accumulated experience and expertise not of one genius, but of many people working together. It works like our cars because of accumulated expertise and experience. And I will refrain from making bad jokes about Dieselgate. But this is a claim about science as a process. I'm arguing that we should believe in science as a process because by and large it has worked well over time. Put another way, we should not trust scientists as individuals, but we do have good reason to have confidence in the process of which they are a part. But this still leads to one remaining important question, maybe a really crucial question. What about any one particular scientific claim? Can we use history and philosophy to give us guidance on when we are probably right to accept a particular claim and when we might be skeptical or cautious? It's very important to be clear that trust is not the same as faith. We know that scientists make mistakes. Yes, there are definitely conspicuous examples of fraud, and there are also conspicuous examples in the history of science of mistakes of a variety of different kinds, some deliberate, some not. The rejection of continental drift, which I worked on early in my career, is a very conspicuous example. It's why I wanted to study it, of scientists coming to a conclusion that they later overturned. But here's an interesting point. We don't abandon trust in our family or friends when they make a mistake, but we do sometimes think about the conditions under which we should trust them. So what kinds of mistakes might be on the lookout for in science? So a few months ago, I started making a list of like the major mistakes, and I thought I would come up with 3 or 4, and I could keep the talk short. Well, there's a lot of different kinds of categories of problems, so I came up with a kind of top 10. I don't have time to talk about all of these today, so I'll just talk about a few that I think are really important for us to think about. So one is fads and fashions. Scientists, like all people, are subject to fashions and fads. There's no question about that. And I do think that journalists contribute to the problem, so we might talk about this in discussion, because journalists often latch onto the latest results that in some cases may not be well tested. So an obvious example of that was cold fusion that got so much scientific and so much journalistic attention before it had really been fully tested scientifically. So the antidote for that, though, is actually pretty obvious. We wait and see. By definition, fads pass, and this is where replication in science comes in. Any really significant result will be tested by others. Now, it may not be replicated in exactly the same way, and there's a big literature in science studies about the difficulty of exact replication, but it will be replicated in at least reasonably comparable ways, and if it can't be replicated, then in general, the claim will be rejected. And this is why it's extremely important, I think, never to place too much weight on any one study, particularly a study that seems very, very surprising or startling. A second problem is hype. There's no question that scientists at times have overpromised. One of the most conspicuous examples that I can remember in my own lifetime was some years ago when the American biologist James Watson was promoting the Human Genome Project, and he said on television that the Human Genome Project would tell us what it meant to be human. And physicists involved in promoting the superconducting supercollider said that if only Congress would give them $4.4 billion, they would find the God particle. And I was very tempted to say, if you give me $4 billion, I'll find the God particle too. So what is the antidote to this? Well, I think that if a claim seems extreme, it probably is. And especially if it's coming from a narcissistic man trying to raise a whole lot of money. But we should also be suspicious of claims that lie outside the bounds of the field of investigation. And this is a really important point, because I am an advocate for scientists speaking up in public. You already heard that. But I'm an advocate for scientists speaking up in public on the matters on which they do science. Because I think that scientists have a good track record in that area, but actually have a rather poor track record when they begin to talk about things outside their areas of expertise. In my opinion, genetics cannot tell us what it means to be human, because meaning is the domain of religion and philosophy and ethics and poetry. Then there's the category of what I like to call nonsense. And there is nonsense in the scientific literature, no doubt about it. And I have had a little bit of fun looking for good examples of nonsense, and you could have a lot of fun with this too. Here's my favorite example. How many of you have heard of the critical positivity ratio? Anyone? Okay, you have to look this up because it's so fun, except it would be funny except that it's true. So in 2005, two psychologists published a paper in the peer-reviewed scientific journal American Psychology. Using equations drawn from nonlinear fluid dynamics, they claimed that the ratio of positive to negative affect at or above the number 2.96835, as measured by a wide range of different parameters, would characterize individuals in flourishing mental health. So you could use this as a kind of test to see whether somebody was mentally healthy or mentally unhealthy. Now, this paper was partially retracted in 2013, so that's 8 years after it was published, but not before it was cited 360 times in peer-reviewed literature and formed the basis of a book. And those citations were not all debunking citations. Now, what is the antidote to this? Well, I would say healthy skepticism. I mean, was it really plausible that one number derived from a totally unrelated field, nonlinear fluid dynamics, could really explain such a huge variety of human conditions? Or that anything involving people could be accurate to 6 figures? Now, it's important to note, of course, that many scientific claims are counterintuitive, so just because something is surprising doesn't mean it's wrong. But if a claim seems totally ridiculous, then it may be, in fact, ridiculous. Then there's the big subject of corruption and influence. And I could do a whole separate lecture on this, but I want to make sure to mention it because I think this is something we may want to talk about. We know that scientists can be inappropriately influenced, and we know that one of the sources of inappropriate influence can be their funding sources. We know that research outcomes can be biased by the desires, the epistemic desires of funders. It's so well documented now that it actually has a name. It's called the funding effect. This has been extremely well documented in research funded by the pharmaceutical industry, where scientists know that the correct answer is that the drug works and is safe and effective. It's also been extremely well documented in the history of tobacco industry funded biomedical research. Now, it doesn't mean that the scientists are committing fraud. They might be, but we have considerable evidence to suggest that many of these effects are subconscious and may creep in, for example, through the mechanism of study design. Now, in theory, peer review should ferret out bias, and there's no doubt that sometimes it does. But we have studies that show that many biased papers pass peer review. So many clearly biased tobacco papers, tobacco-funded papers, were published in leading biomedical journals, including the Journal of the American Medical Association, The Lancet, the British Medical Journal. So this is not just an American problem. Bias can be subtle. It can be hard to detect. So peer review is a necessary but not sufficient condition for ferreting out bias and building trust. And this is one reason, among others, why disclosure matters. So a couple of years ago, with a group of colleagues from a wide variety of disciplines, including research on tobacco, research on pharmaceuticals, research on endocrine disrupting chemicals, we published this article, Why Disclosure Matters. And we argued that it matters for a number of reasons, but one is that so that any reviewer, editor, or user of the information could be alerted to potential bias and maybe would look a little bit more closely, for example, at study design than you otherwise would, but also, and perhaps even more importantly, so that scientists themselves are reminded that they are in fact subject to bias and need to pay attention. And one of the clearest pieces of evidence of this comes from a big study that was done in the United Kingdom, where they asked biomedical researchers, do you think that your work would be biased if it were funded, let's say, by a pharmaceutical company? And something like 90% of them said no. But then they asked the question, do you think that your colleagues' research would be biased? And 60% said yes. So psychologists actually have a name for this. It's called the third-party effect. We think that other people are biased. We think that other people are influenced by advertising, but we aren't influenced by those things. That's just something that other weak people are subject to. But the reality is we all are, and the scientific evidence shows it. Then there's the issue of racial and gender bias. Again, these are all big topics, so I'm just touching on them here, so if we want to pursue it more in the conversation, we can. But historians of science have amply documented how racial and gender bias have affected scientists throughout the history of science. My favorite example is to do with gender bias in science. I talked about this in Berlin 2 days ago. It's been a long week. It's been a long year. 2 days ago, one of my favorite examples is a theory called the limited energy theory. Have any of you ever heard of this? No? Okay, if you're interested, the WBZ recorded my talk on Monday, and I talked about it at length. So this was a theory that was very prominent, promoted in the 1870s, to say that if women were educated and subjected to the rigors of higher education, their brains would grow, but their uteri and other reproductive organs would shrink, and they would become infertile. Now, you may laugh, but this was a very influential theory, taken very seriously by educators and scientists, and it was presented as a deductive consequence, a hypothetical deductive consequence of the first law of thermodynamics, conservation of energy. So it seemed like it had a very robust scientific pedigree. But the giveaway was that it only applied to women. No one stopped to ask that if men got educated, which of their organs would shrink? Now, racial and gender bias are subsets of what I've called cultural seepage, a more general phenomenon where cultural pressures affect scientists' thinking even when they think they don't. And again, a big topic. This is a very complex topic, but one antidote for it we have evidence to support is diversity. That is to say, when you have a diverse community of scientists, they're more likely to point out certain logical flaws, like a theory that applies only to women and not men, even though it's supposed to be a universal law. So it's one of the reasons why diversity in science is so important. It's not just because it's morally correct or we're trying to do the right thing or be politically correct. It's because a diverse community is actually likely to have more likely to have intellectually robust results. Diversity makes our science better because a diverse intellectual community is more likely to recognize and call out bias and cultural seepage than a homogeneous one. How much time do I have left? I have like 5 minutes? Yeah, okay. So maybe I'll leave it at that because I could go on at length about any of these issues, but this is sort of a lot of details that maybe are more than we need right now. So, but the general point I want to bring is that many of these things are actually well illustrated through the history of science. So this is a shameless plug for my own field. When we examine the history of science, we come to understand better how some of these problems like bias and cultural seepage, how they develop, and why they can be so hard to root out. So one of the things I've always said is that one of the reasons we need history is that we need to be interested not only in what's new and exciting in science, because science funding agencies are always interested in the cutting edge, the breakthrough areas, the novel claims, and that's all good, that's all important. That's the frontier of science, and it's where learning happens. But we also need to know what's old and established and might be incorrect. We need to have a mechanism for always thinking about the fact that some of our assumptions may not be correct. Or as I like to say, there's an old saying that I don't know where it comes from, but that there are two frontiers of knowledge, that which we are about to discover and that which we discovered long ago and are about to forget. So let me just then go to the end here. Oh, let me say a little bit about GMOs. One of the other things that I think is important, so one last point, is about the problem of overgeneralization and overreach. So scientists tend to be ambitious people. We want our theories and our results to be broadly applicable. But I think this sometimes causes us to overreach. And I think this is quite clear in some claims that have been made about genetically modified crops. So I want to just say, first of all, a certain disclaimer. I have not worked on the problem of genetically modified organisms. I have not analyzed the scientific literature. So in discussing this example, I'm not taking a position on GMOs, but I am taking a position on some things that people have said that I think constitute overreach. So I have heard many distinguished scientists say in public that GMOs are safe, period. I have also heard distinguished scientists say that when the public doesn't like GMOs or asks for labeling on food, that, quote, the public are being irrational. And I would argue that the first claim is misleading because it's overgeneralized, and the second may be a misinterpretation of people's concerns. So if we say GMOs are safe, well, that can mean a lot of different things. We could be asking, are they safe to eat? We could be asking, are they safe for the environment? We could be asking, are they safe in terms of the concentration of power over the food supply in the hands of a small number of people or companies? We could be using that as a cipher for, are they a good idea? These are all very different kinds of questions, and they take different kinds of expertise and different kinds of thinking to answer. In my opinion, it's not helpful when scientists overgeneralize. And given that a good deal of GMO research is industry funded, particularly in the United States, citizens do have some warrant for wondering about funding effects, some warrant for skepticism, especially when they hear such overly broad claims. And moreover, and this is an important point, many people oppose genetically modified organisms for reasons that have nothing to do with food safety. So in the United States today, the industry is trying to say this is an issue of food safety. The scientific evidence says that they're safe to eat, and therefore there's no problem. But there are many people who are opposed to genetically modified organisms on grounds that have nothing to do with food safety. One of them is Pope Francis. And if you're interested in this, his encyclical on climate change has an interesting discussion of why he's opposed to genetically modified crops. Now, these reasons may be good or they may be bad. You may agree with them, you may disagree with them, but they're not irrational and they're not anti-science. Okay, so as I've said, there's a long list. I don't have time to discuss all of these, so I'll just now go to my conclusion. My father was a biochemist and an immunologist and a very smart man. And one of the things he told me when I was very young, which may upset anybody here who might be from the pharmaceutical industry, but I actually think he was right, take no drug that has been on the market for less than 7 years unless it is for a fatal disease. Now, why did my father say this? Well, there were two reasons. One, in 50 years as a biomedical researcher, a PhD scientist, but not a physician, he had witnessed 50 years of drug industry influencing of physicians' prescribing practices. He knew that many doctors didn't have time to read the scientific literature and relied on materials that they got from the pharmaceutical industry. And long before the opioid epidemic in the United States, my father recognized that this was problematic. And we're seeing this now in the United States, where we're learning that huge numbers of physicians prescribed opioid drugs to their patients based on pharmaceutical industry reassurances that these were safe and not addictive, even though now we know that they are, in fact, highly addictive. And right now in the United States, more people are dying from opioid-related overdose than from gun violence. So this is a really serious issue. But the larger issue, the one that my father was more concerned about, was actually the second one, that most clinical trials are just too small and too short to reveal all the possible side effects in large, diverse populations. Clinical trials are obviously extremely important. This is not to say that clinical trials aren't important. but to make the point that many physicians know that it's only when a drug is widely used in diverse populations under diverse real-life conditions that doctors come to know fully what it can and can't do and what the side effects are. So I think we can say something similar about science. Peer review is like a clinical trial. It's the first step in testing a knowledge claim. It's a critical test. It's an essential test. But the most important test of scientific claims are what happens when people use them. This, of course, was the conclusion of pragmatist philosophers who saw truth as a process rather than a product, an evolving condition rather than a fixed state. So the great American pragmatist philosopher William James wrote more than 100 years ago, "Experience has a way of boiling over and making us correct our present formulas. The absolutely true, meaning what no further experience will ever alter, is that ideal vanishing point towards which we imagine that all our temporary truths will someday converge. Meanwhile, we live today by what truth we can get today, and be ready tomorrow to call it falsehood. Ptolemaic astronomy and Euclidean space were expedient for centuries, but human experience has boiled over those limits, and we now call those things only relatively true, or true within those borders of experience." In short, science does not give us absolute truth, but it does give us knowledge consistent with the borders of our experience, knowledge on which we can reliably act in many cases. Ptolemaic astronomy was not absolutely true, but it did make accurate predictions of the motions of the planets. Or put another way, time may not heal all wounds, but it does sort out many epistemic claims. And finally, if we return to Pascal, we can ask, what are the consequences of accepting a claim if it's false versus the consequences of rejecting it if it's true? And when we put it this way, then we come to understand so clearly why we must act on climate change. Because with respect to climate change, we should accept the claims of climate scientists, because if we don't, and they're right, the consequences will be dire. And if it turns out to be a big hoax, well, then we will have created a better world for nothing. Thank you very much.